Okay, guys, good evening and welcome back to our channel. In today's class, we want to look at solving of CHM260 past question last year. All right, so we have 35 questions here. So let's see how far we can actually exhaust this question. We have a target of 30 minutes. So let's see if we can beat the time and run it in less than 30 minutes. All right, the first question here. I'll be reading out the questions at the same time. I'll be displaying the questions on the screen. Okay, so the first question here says, the transmission of polar effects through pi bond is called dash. Now, the transmission of polar effect through pi bond, the answer to this question is mesomeric effect. Okay, that's mesomeric effect. Now, question number 2 says, which of the following is most basic? Right, we have CH3, we have CH3, CH2, we have Cl, CH2, CH2, NH2. Now, the answer to this question is ethylamine. Now, why is this ethylamine the most basic? Is because the ethyl is more of a plus I. It's more of positive inductive effects than the methyl. So this is actually the most basic. Now, this is actually not going to be more basic because we have fluorine, which is going to be exhibiting minus I effects. Remember, the presence of a minus I substituent in a base decreases the basic strength. So the answer to this question is ethylamine. Okay, now let's start the number 3 question. So take note of this. The second question is ethylamine. Okay. Now question number 3 says the compound CH3, CO, CH3 can also exist as CH3, C, OH, CH2. This phenomenon is known as dash. Alright. Now this compound you're seeing here is actually propanol. And this compound you're seeing here is propanol. Propane 2-ol, rather. So the OH that was inside the bracket is placed here, and we have CH2. Now this process is what we call tautomerism. This process is said the compound, this can also exist as this phenomenon is called tautomerism. So the answer to that number 3 question is tautomerism. Okay, now let's start number 4 question. Number 4 says, draw the structure of a positional isomer of 2-butanol. Draw the structure of a positional isomer of 2-butanol. Now, 2-butanol is CH3, CH2, CH, OH, and CH2. Now, positional isomer is a type of isomer whereby the functional group takes a different position, right? It's a type of isomerism whereby two compounds with the same molecular formula differs in their structure based on the position of the functional group. So, if this is butan 2-ol, the positional isomerism or isomer of this compound would be butan 1-ol. So we have this to be CH2, CH2, CH, OH. So butan 1-ol is a positional isomer of 2-butanol, which is essentially butan 2-ol. My question says, what is a type of isomerism exhibited by 2-methylpropane and N-butane? They say the type of isomerism exhibited by 2-methylpropane and N-butane. Now let's draw the structure. This is C, C, and C. We have CH3 here. We have CH3. We have CH3. We have this. Alright. Now this is C4H9. Now when they say N means normal, it means it's a straight chain. So this is CH3, CH2, CH2, and CH3. Now this is normal butane. Now these two compounds, if you check it out, they have the same molecular formula C4H10. Now the type of isomerism is chain isomerism because their chain is not the same. This is a straight chain and this is a branch chain. So the two are called chain isomers. So the question says, what type of isomerism is exhibited between these two? It is chain isomerism. Okay, number 6. 6 says, draw the structure of 2-butanol. 2-butene 1O. Now, this is basically an organic compound that has 4 carbon chain and a double bond at position 2 and OH at position 1. So we start by saying 1, 2, 3, and 4. Right? So this is carbon 1, 2, 3, and 4. Now, 2 butane, this 2 is for this A. A makes a double bond. So you put your double bond there, counting from the right hand side. As carbon 1, you have OH. Alright? So you have this. For me to now add the number of hydrogen, what I'm going to say, I'll subtract the number of bonds on each carbon from 4, because carbon can take maximum of 4 bonds. So here it's going to be 3, here it's going to be 1, here it's going to be 1, and here it's going to be 2. So this is a structure of 2-butane 1O. Okay, now question number 7 says, provide the structure of 2-propane thiol. 2-propane thiol. Give the structure of 2-propane thiol. 2-propane. Plus, thiol is compound that functional group. The functional group of thiol is SH. So what they simply means is that write the propane, then go to number 2 and put SH. So this is 1, 2, 3. This is CH3, this is CH2, and this is CH2. This is propane. But if I want to put the thiol is SH at carbon 2, so I'll reduce the number of hydrogen here, and then I put SH. So this becomes 2-propane thiol. That is the answer to that. Okay, now we have number 8 question. Number 8. Now number 8 question says, give the structure of the compound formed when 2-butanone. Give the structure of the compound formed when 2-butanone is treated with zinc amalgam in hot HCl. Give the structure of the compound when 2-butanone. Now 2-butanone is CH3, CH2, C double bonded to O, and CH3 is treated with zinc amalgam. Zinc amalgam is zinc, amalgam is mercury. We have hot HCl. Now this reaction is the Clemmensen reaction of aldehydes or ketone. Clemmensen reagents and Wolff-Lechner, they convert aldehydes and ketone directly to hydrocarbon by converting this CO to CH2. So what we have here becomes CH3, CH2, CH2. Now the work of this is to convert this CO to CH2. So this is the reaction. This is butane, and this is 2-butanone. That's question number 8. Now question number 9. Question number 9 says, what organic compound can be obtained from the hydrolysis of acid and hydride? What organic compound can be obtained from hydrolysis of acid and hydride? Now, acid and hydride is basically 2 acids, 2 carboxylic acid coming together with loss of water. Alright, so hydrolysis simply means you break the acid and hydride involving water, using water. Now, the formula for acid and hydride is this. Right? Now, if I react this guy with water, now look at what is going to happen to me. Water is OH and H. So I'll come here, I'll come to any part of this. When I break this guy, this side I'll add OH. This side I'll add H, and this other side I'll add OH. So this becomes this side here that has 2 O. This and this, I'll put H. The side that has just 1 O, I'll put OH. So this becomes RCOH plus another RCOH. That means that if you hydrolyze acid and hydride, hydrolysis of acid and hydride will give us 2 molecules of carboxylic acid. Because it is 2 molecules of carboxylic acid that will come together to give us anhydride. Anhydride means no water. So when you hydrolyze acid and hydride, you break the bond using water, you're going to have 2 molecules of acid and hydride. Okay, so this is the answer to that question, 2 carboxylic acid. Question number 9. They say, number 10 rather. They say, which derivative of carboxylic acid is the most reactive? Now, carboxylic acid derivative. Now, this is carboxylic acid. The derivative of carboxylic acid can be said to be, and this is ester, this is amide, this is acid fluoride, this is acid anhydride. Now, the most reactive of the derivative is acid fluoride. So somebody asks, which of the derivative of carboxylic acid is the most reactive? It is the acid fluoride. Okay, bear in mind that these are the derivative of carboxylic acid. We have ester, this is amide, this is acid fluoride, and this is acid anhydride. Okay, now question number 11. Question number 11. Give the structure of the amide formed by the reaction of methylpropanoate and ammonia. Give the structure of the amide formed by the reaction of methylpropanoate and ammonia. Now, this reaction falls under reactions of esters, right? Now, esters actually can carry out several reactions. One of them, which is ozonolysis of esters. Ozonolysis is a process where ester reacts with ammonia to give amides. So, methyl is said, give the structure of the amide formed by the reaction of methylpropanoate. Now, this is the structure of methylpropanoate. CH2COO CH3 plus ammonia. Now, let me break this guy down further. And ester is this. Alright? Now, what I'm simply going to do is that if I break down ammonia, this is NH2. So replace this guy with NH2. When this guy comes out, it will pick out the H and form alcohol. Ammonolysis of ester will give us amide and alcohol. So when you move this OCH3 and replace this guy with NH2, what we are going to have here becomes CH3, CH2, C double bond H2O, NH2 plus this CH3O pick up the hydrogen and form ethanol. So the amide that will be formed is propanamide. This guy is methyl propanoate. Okay, now so question number 12 says cyclic amide. Cyclic amide is called lactams. Cyclic amides are called lactams. Plus, let me use this opportunity to tell us about cyclic esters. Cyclic amides, lactams, are cyclic amides. We also have what we call the lactones. This is cyclic esters, just in case you're being asked. Okay, here is question number 13. Draw the structure of benzoic, ethanoic, and hydride. Draw the structure of benzoic, ethanoic, and hydride. Class 4. Now, this anhydride is actually what we call mixed anhydrides. They're actually coming from 2-carboxylic acid. Now, first, what is benzoic acid? Benzoic acid is this. OOH. This is benzoic acid. What is ethanoic acid? Ethanoic acid is CH3, COOH. Now, class, anhydride means loss of water, and hydrous means without water. So if I want to form these two guys, I'll mix two of them, and then I'll remove water. So what will I do? Please pay attention and look up. I'll rewrite this like this. And then I'm going to turn this compound so that the COOH will face the other side. So I'll come here, I'll say, this is going to be OCCH3. This is ethanoic acid, but I just had to reverse it. Now this becomes this. Now, anhydride means 2-carboxylic acid coming together to lose water. This is benzoic acid, and this is ethanoic acid. So when they come together, remove water from here. Water is H2O, so I'll take OH from here, and I'll take it from there. Once I do that, if I pull out this water here, when I pull out water, this is what we are going to have. Well, if this guy goes on leaving us with oxygen in the center. So, ladies and gentlemen, benzoic, ethanoic anhydride is what we have on board. But bear in mind that this ring, most of the times, can be written as C6H5. So I can write this into the C6H5, C double bonded to O, C double bonded to O, and CH3. These parts came from the ethanoic acid, and these parts came from the benzoic acid. Okay, so let's look at the next question. So this is the structure of benzoic, ethanoic anhydride. The next question here says, the effects that an atom or group of atoms has on electron density by virtue of its electronegativity is called the effect that an atom or group of atoms has on the electron density by virtue of its electronegativity is called inductive effects. Alright, the answer to that question is inductive effects, because inductive effects arises due to electronegativity difference between two atoms forming a sigma bond. So the answer to number 14 is inductive effects. Now number 15 says, a phenomenon, okay, that number 14 is inductive effects. Let's just write it out. Number 14 is inductive effects. Now number 15 says, a phenomenon where there is an overlap of pi orbital with adjacent sigma orbitals to form extended orbitals is known as hyperconjugation. So the answer to that question is hyperconjugation. So if you notice, this past question was last question. They asked question based on inductive effects. They've asked question based on isomeric. They've asked question based on hyperconjugation. So therefore, as you're revising your notes, don't disregard these effects. Now, number 16 says, a chiral molecule and its mirror image. A chiral molecule and its mirror image represents a pair of stereoisomers called a chiral molecule and its mirror image represents a pair of stereoisomers called enantiomers. Okay. Now they say, which of the following compounds contains chiral carbons? Which of the following compounds contain chiral carbons? That's question 17 says, which of the following compounds contain chiral carbon? We have 3-pentanol. We have 3-chloro-1-butene. We have 3-phenyl-2-butanol. We have 1-chlorobutanol. So let's label this guy 1, 2, 3, and 4. So I'm going to be taking the structures one after the other. Now, for the compounds we called, for a chiral carbon, they said, which of the following compound contains a chiral carbon? Of course, a chiral carbon is a carbon atom that has 4 different substituents. So we're going to write out the structures of all these guys and check the carbon one after the other and see if there will be at least one of the carbons that has 4 different substituents. Now, the first one is 3-pentanol. Now, penta means 5 carbons, and at carbon 3 you have O, that's OH. So this becomes 1, 2, 3, 4, and 5. Right? If you number this guy from whichever direction, here is going to be number 3. So if you put your O, here becomes CH2, here becomes CH3, here becomes CH, here becomes CH2, and here becomes CH3. Now, this carbon here, the first carbon, remember, I'm not just going to jump to the center. I want to take the carbon one after the other. This is carbon 1, 2, 3, 4, and 5. Carbon 1 is not a chiral carbon because you can see the presence of 3 same type of atom. That is hydrogen. So carbon 1 is not. Carbon 2 is not because you can see 2 same type of hydrogen. Now, carbon 3 looks like a chiral carbon, somehow convincing, but it's not a chiral carbon because this right-hand side is CH2CH3. The left-hand side is also CH2CH3. So these two substituents on both sides are the same. So this carbon that looks like a chiral carbon is not a chiral carbon. So we call this guy ethane base, right? We're trying to convince you to say that this guy is a chiral carbon. So this compound, carbon 4 has no chiral carbon, carbon 5 is not. So therefore, this entire compound does not have a chiral carbon. This carbon 3 that looks like a chiral carbon is not, because this ethyl on the right hand side is the same thing as the ethyl on the left hand side. Remember, a chiral carbon must have 4 different substituents on it. So that first guy is not a chiral carbon. So let's look at the next one. The next one is 2 chlorobutes, 1A. 3 chlorobutes. So butane is 1, 2, 3, and 4. Alright? Now, 1 butane means there's a double bond at carbon 1. So let's get there 1, 2, 3, and 4. 3 chloro means there is a chlorine here. Now, let's complete this guy. We have CH3 here. Here will be CH3 because there is 1 bond here. So this guy, 4 minus 1 is 3. You put your H here, and here is H, and here is CH2. Obviously, we have a chiral carbon here. Now, this is carbon 1, 2, 3. Carbon 1 and 2 can never be a chiral carbon because they contain a double bond. Carbon that contains a double bond cannot be a chiral carbon. Carbon 4 cannot be a chiral carbon because it has same type of substituent. But carbon 3 is a chiral carbon because this everything here is seen as one substituent. This is seen as another substituent. This is seen as another substituent. This is seen as another substituent. So if you take a careful look at these 4 substituents, they are all different. So therefore, carbon 3 is a chiral carbon. So therefore, this guy contains chiral carbon. So this is not, this guy contains. So let's look at the next one. 3 phenyl, 2 butanol. 4 butanol is the parent chain, 4 carbon. So we have 1, 2, 3, and 4. 1, 2, 3, and 4. You get all this guy. Carbon 2, there is all because this guy says 2 butanol, right? Carbon 2, there is all in here. And carbon 3, there is a phenyl. Phenyl is C6H5. So this is C6H5. So you complete this ID, this is H to be there. This is H here. This is H here. This is CH3. Let's say we've got 2 chiral carbons here. Now, so this is 1, 2, 3, and 4. Carbon 1 is not a chiral carbon. Carbon 2 looks like a chiral carbon. Obviously, yes, it is a chiral carbon. Because this carbon here has this 1 substituent, 2 substituents, 3 substituents. Everything here is counted as 1. So this guy has 4 different substituents. The OH is not the same as CH3, CH is not the same as H, and this is not the same as everything here. So carbon 2 is a chiral carbon. Alright, so let's remove this circle and then look at carbon 3. Hopefully, we're going to get another chiral carbon there. So we have this. So let's talk about 3. Once again, we have the chiral carbon. This guy is not the same as this, is not the same as this, and it's not the same as this. So we have 2 chiral carbons in this compound. So this guy contains 2 chiral carbons. Now the next one is 1 chlorobutane. 1 chlorobutane. So let's say butane is 4 carbon 1, 2, 3, and 4. At carbon 1 we have chloro. Now, if you complete your CH3, this CH2, and this CH2, and this CH2. Now, this is not a chiral carbon because it has 3 same type of atom. This is not a chiral carbon. This is not a chiral carbon. This one that looks like a chiral carbon is not because it has 2 same type of hydrogen. So therefore, the 2 compounds that contain chiral carbon are 3 chlorobutane and 2 phenyl 2 butanol. Okay. So let's start to the next question. Question number 18. They say, give the structure of the product. Give the structure of the product. Give the structure of the product of the complete oxidation of 2 propan 1 ore. give the structure of the products of a complete oxidation of 2-methyl propan-1-ol. You're being asked to give the product of a complete oxidation of 2-methyl propan-1-ol. So let's put up the structure. This is CH3, CH, CH2, this propan plus. This is an alcohol. Alcohol, we have primary alcohols can be oxidized to aldehyde, which can further be oxidized to carboxylic acid. Secondary alcohols can be oxidized to ketone. Now, so anytime you are asked to actually show oxidation reaction of an alcohol, the first thing you're going to do is to verify if that alcohol is a primary alcohol. Now, of course, you can see this question is a primary alcohol because the carbon bearing the OH is only attached to one other carbon. So this is a primary alcohol. And primary alcohol, the end product of primary alcohol is always carboxylic acid, right? So basically, what I'm going to do is that I'm going to convert this entire line. It also move down to carboxylic acid. It's supposed to, the first one is supposed to give us aldehydes, and then from aldehyde we get to carboxylic acid. But since the question said, give the complete, so there is no need going to the aldehyde stage. I'm just heading to the carboxylic acid stage. So here, the CH2OH will be converted directly to COOH, straight up. Oxidation, I put this, so this becomes CH3, CH, CH3, COH. That is it, COH. So if this is this 2-methyl propan-1 or this 2-methyl propan-1 or this will now be 2-methyl propanoic acid. Okay, so that is that for that question. Now the next one is saying ethers are more soluble in water than alkenes of the same number of atoms. True or false? It's true because ether can form hydrogen bonding with water. So the answer to that question is true. Ethers are more soluble in water because they can form hydrogen bonding with water, right? But they cannot really form with themselves like that. Now this is the structure of ether. So ether is this. Ether has oxygen, and when it reacts with water, water is something like this. So the hydrogen of the water bonds with the oxygen of the ether. So they can actually, in the case of alkanes does not have oxygen that will further, facilitate their hydrogen bonding. So ethers are more soluble in water than alkanes of the same number of carbon. True. The answer is true. Now question number 20 says, question number 20 says, which of the following haloalkanes has the highest boiling point? Which of the following haloalkanes have the highest boiling point? We have CH3, we have I, we have CH3, we have A, we have CH3, we have Cl. Alright, so the next one says 21. Draw the structure of S to bromo propanoic acid. Now this simply means that this compound contains a chiral carbon. And the chiral carbon has the configuration of S. And S configuration means that the rotation, some kind of, is moving towards the left hand side. So but before we do that, let's see how to get the structure. Now, first, let's interpret the structure of this before we start adding the S. 2-bromopropanoic acid. This is 1, 2, 3. Propanoic acid, carbon 1 is COOH, carbon 2 is bromo. You have CH3 and you have H. Now, this chiral carbon is what we are asked to give the configuration. Now, S means left hand side. S means the R is going to rotate to the left. So let's reposition this guy to give us our left movement. So for me to do that, I'll come here. I'll put BR here. And I'll put COOH here. Now, why am I doing that? Now, let's assign priority to this option. Bromine has an atomic number of 35. Carbon has an atomic number of 6, and this guy has 6, and this guy has 1. 35 is higher than this guy, so I'll give 35A the highest priority. Now, carbon is 6, there is a tag. You look at the next substituent is oxygen, 8. The next substituent is hydrogen, 1. So 8 is higher than this guy. So because of this, we're going to give this one the second priority, B. And this one becomes C because carbon is 1, hydrogen is 1. Carbon is 6, hydrogen is 1, so carbon is high. So when you draw the arrow, you move from the highest, pass through B, and come here. So class, this is S. When the arrow moves anti-clockwise, it is the S. So the answer to this question is this structure we have here on the board. Please, you can look up to the channel because we've already made a video on how to assign R and S. So if you want to really understand how this actually came about, you can check the video. The link is actually on the comment section. So just click it, or in the description box. Just click it and then watch on how we can get R and S of a compound. So this is the structure of this. When you're asked to do this, always make sure that you put this indication for the lecturers to actually find it very easy to do it faster. Okay. So that is question. Let me pause. Let me review my map. All right. So let's start question number 23. They say, which of the following will have the highest pKa value? Which of the following will have the highest pKa value? We have 2-chlorobutanoic acid. We have butanoic acid. We have 2,2-dichlorobutanoic acid. Now, it is important for us to know that pKa, just like we have pH, pH is used to determine the strength of mineral acid. Low pH means high acidity, and high pH means low acidity. Same things are applicable to pKa. Right? If the value of pKa is low, it means high acidity. High pKa means low acidity. So for them to ask us to assign to check which of them have the highest pKa. Highest pKa is equivalent to saying least acidic. So let's check out these three guys to see which one will be less acidic. Class. Now we're going to use the concept of inductive effect. Now all of them here, they are all 4-carbon acid, butanoic acid. All of them. Now recall that in inductive effects can be used to actually check the strength of carboxylic acid. The presence of a minus I substituent on the chain increases the acid strength. So now, 2-chlorobutanoic acid. This one has one minus I group. It has one minus I group. Now, this 2,2-dichloro has 2 minus I group. So when it comes to acidity, the one that have 2 minus I on carbon 2, this will be the highest. This will be highest acidity. Highest acidity. Because why is this guy higher? Because it has 2 minus I, negative inductive effect substituent, that is the chloro. Followed by this guy. The one that will have the least acidity is the butanoic acid. Because this butanoic acid does not have, there's no minus I substituent on that. So this will be the least acidic. So therefore, butanoic acid, being the least acidic, will have the highest pKa value. So that's the answer to that. Highest pKa value means the least acidic. Lowest pKa means the highest acidic. As me, the question I say, which of these will have the lowest pKa? It shall be 2,2-dichlorobutanoic acid. Okay, the next question. The next question says, draw the structure of E isomer of 2-butene. They say draw the structure of E isomer of 2-butene. Now, 2-butene means 4 carbon with a double bond and carbon 2. So I'll just put 2 carbon here. I'll put this. Now E means 2 higher priority substituents from the 2 carbons with a double bond on the opposite side. Right? So if I come here, I put CH3 here. I come here, I put CH3 here. I come here, I put H. I come here, I put H. So this is E isomer of that, right? Okay, so this is the E. But in case you're wondering, how do we arrive at this? First and foremost, you can first of all write the structure of 2-butene, which is CH3, C double bond C, CH3. This. Now, you can now transform this into their geometric form. Put the 2 carbon of the double bond at the center and raise this. This carbon has 2 substituents. So CH3, we put CH3 here and H. On this carbon, this takes the higher priority. So it means that the second higher priority substituent must be down if I must get my E. Because E stands for opposites in JJ. Okay, so this is the E isomer of 2-butene. What did they attach on for this Z isomer? The Z isomer would have just been flipping one side. So I'll come here, I'll take H up, and I'll bring CH3 down. Please bear in mind that this is our Z. Bear in mind that E is sent in as strands, while Z is sent in as what? Sieves. Just in case they replace this E and you're asked to actually give strands, E is this. Methyl is the higher priority of this carbon, so methyl here will be on the opposite side. In this case, methyl is on the same side. That's how we have to say. Okay, so the next question here is draw the structure of NN dimethyl butanamide. NN dimethyl. Now, butanamide is CH3, CH2, CH2CO, NH. This is butanamide. But on the end, we have dimethyl. So this is CH3 and this is CH3. Right? So since 2 substituents are on the end, we say NN. This is equivalent to saying if 2 substituents on the same carbon, you can say 2,2-dimethyl. So that's the same way we say NN. Please bear in mind that this is stationary amide. This is stationary amide. Amide where the end has 2 carbons is stationary amide. Alright? Okay, so here is provide the structure of ethyl methyl sulfide. It's very simple. Ethyl is CH3, CH2, methyl is CH3. Sulfide just puts S at the center, and that becomes sulfide. Remember, this guy is also known as thioether. Thioether has a general formula of this, segment of this. So this is ethyl methyl sulfide. If they had said disulfide, you would have added 2 sulfur at the center. This is what I mean. They have said disulfide, you would have simply say S, S, then add whatever the alkyl groups are. Now we have the next question here. They say, what is the name of the compound? What is the name of the compound formed when ethyl acid is reacted with propanol in the presence of acid catalyst? Now that is a esterification reaction. But let's write it out. Now they say when ethyl acid CH3COOH plus propanol CH3 CH2 CH2OH. Now in the presence of an acid catalyst, so we just put H plus here. Now look up. Basically what we are going to do here is to relate this OR with this. So pick up this OH and take this H here and form the water. Then pick this O and join it to this other O. So this is going to be CH3, this guy, CO. This is it. Then come here, join this, start from this O. O, after O we have CH2. After CH2 we have another CH2. After CH2 we have CH3. Plus This OH that will come out of here will pick out this H and form water. So this is ethanoic acid, and this is propanol. So this is propyl ethanoic. So they asked us for the name of the product or the compound. You must give them the name. This is propyl coming from propanol. This is ethanoic coming from ethanoic acid, and then you have your water. The backward reaction is what we call hydrolysis, and this forward reaction that gives rise to this product is what we call esterification reaction. Now, question number 28 says, question number 28 says, give the structure of the major products. Give the structure of the major products. Give the structure of the major products formed when the product of ozonolysis, of 2,3-dimethyl-pentane is subsequently treated with zinc in acetic acid. Now the question will be displayed on the screen, so you can read out the question for yourself. Now they say 2,3-dimethyl-pentane. Now we have 1, 2, 3, 4, and 5. 5 carbon atoms. Now page 2 means there is a double bond at carbon 2. So I'll come here. Alright. And then we have 2, 3 at carbon 2 and 3. We have this. Okay, so this is now ozonolysis followed by treatment with zinc and acetic acid. This is acetic acid, zinc. Class. Remember this reaction, you guys did this in the 132, reactions of alkenes, condensation reaction. Right? Now when ozone is treated with a double bond, it divides the double bond into two. Now, since this carbon is not having any hydrogen, I think this carbon was having hydrogen. After cutting this guy into two, it will convert this guy to carboxylic acid. But in the presence of this zinc, it will convert it to alkynes. But since the both carbons of the double bond does not have any hydrogen, after cutting this bond into two, it will convert it to a ketone. It converts it to what? A ketone. So this becomes CH3, CH2, C, CH3. Ketone means simply add O here. Plus, we have this C, CH3. So since there is no hydrogen on this carbon, after putting this into two, this oxygen will just stand there to form a ketone. Now, if you want to write this guy appropriately, how will I write this? This is butan 2O. CH3, CH2, C double bonded to O, CH3. This is carbon 1, carbon 2, carbon 3, and carbon 4. 1, 2, 3, and 4. And this is propanol. CH3, this, and CH3. Okay, so take note of that. The reason why you are giving ketone is because this carbon of the double bond, none of them is having hydrogen. So after cutting it into two, you simply need to add O to this, and that is final. Okay, question 29 says, aldehydes with no alpha hydrogen can undergo self-addition, true or false? The answer is false. Aldehydes with alpha hydrogen are the ones that can undergo self-addition. Those kind of additions are called the Aldol condensation. Let me give you an example of what an alpha carbon is, or alpha hydrogen. Now, let's assume this is an aldehyde. Now, this aldehyde functional group is actually this C. The first carbon attached to this guy will be the alpha carbon. Alpha is always the first. Alright, so if this is a reference point, the first guy attached to this guy is alpha. So this is alpha carbon. Now this aldehyde contains a hydrogen here. So this type of aldehyde can undergo Aldol condensation, that's self-addition. But if you want to deplete all this hydrogen, I'll come here and put carbon here. Come here, I put another carbon here. Come here, I put another carbon. Yes, in as much as this is still an aldehyde, but the first carbon directly attached to the aldehyde functional group, which is this alpha, does not have any hydrogen, and this guy cannot and will not be able to undergo self-addition, known as Aldol condensation. So the answer to this question is false. They say aldehydes ignore alpha hydrogen can undergo self-addition reaction. The answer is false. It's only those ones with alpha hydrogens that can undergo self-addition. And don't forget that alpha hydrogens are the hydrogens on the alpha carbon. And what is the alpha carbon? The first carbon directly attached to the aldehyde carbon. Or in the case of the ketone, the ketone. The reduction of cyanobutane with lithium tetrahydroaluminate 3. The reduction of cyanobutane with lithium tetrahydroaluminate 3 gives that. Fine, cyanobutane is sent as saying butyl cyanide or pentane nitrile. Now this is CH3, CH2, CH2, CH3, this is butane. And then we have Cn. Don't forget that this Cn has a triple bond between the carbon and the N. Now, lithium tetrahydroaluminate 3 is lithium aluminum hydride. This is this guy. Class, if you could remember, in this reaction, this is reaction of nitro. When this guy reacts with lithium aluminum hydride, it reduces this guy to amide. It's going to reduce this guy to amide. What do I mean? This guy will move all of the first double bond, put H on both sides, put H here, put H here, remove the second guy, put H here, put H here, and then you have amide. So when you do this, this becomes CH3, CH2, CH2, CN. So this becomes, you put H up, you put H down, put H up, put H down. That means if you remove this bond, you put 2H, remove this other bond, you put 2H. So when I want to write it properly, I'll now say CH2, NH2. So that is the answer to that guy. So this is cyanobutane, which can also be named as pentane nitrile. If you're naming it as pentane nitrile, you count from the carbon of the cyanide. 2, 3, 4, 5. This guy is 1, 2, 3, 4, 5. This is pentane amine or pentyl amine or amino pentane. So these are the three names for that guy. Now the next question says the reaction of aldehydes with hydroxylamine will give the corresponding dash. Now it's going to give us an long sign, right? The reaction is going to give us an long sign. If you could remember the reactions of aldehydes and ketones with derivative of ammonia, that's condensation reaction. You can check our playlist organic chemistry, condensation reaction of aldehydes. You're going to find the reaction there. So when we have the same, when an aldehyde, now in this case now, it's not really necessary that you give them the reaction because they will not be specific of the aldehyde. Only told us that when an aldehyde reacts with hydroxylamine, what is it going to give us? Now this is an aldehyde. We have this. Remember, aldehydes are written as CO, this. But I want to write it this way so that you can see how the reaction is going to take place. This is hydroxylamine is NH2OH. Now this is going to form condensation reaction. Take these two hydrogen, take this one off street and form water. When you do that, the product becomes CH, double bond, and OH. Now the answer to that guy is opposite. Alright, so the product is going to be an oxide. Okay. Now, the next question says, what is the name of the product formed when butyl benzene is oxidized? We have this. This is CH2, CH2, CH2. Now remember, this is always oxidizing potassium tetraoxide manganese, hot. As long as this carbon, the first carbon attached to this benzene, as long as it has one hydrogen or more, everything here will be converted to COOH. Right? We call this type of oxidation the relative oxidation. As long as this carbon is called a benzyl carbon. So far as this carbon is having at least one H, everything here, irrespective of how bulky it seems to be, converts to COOH. So this is butyl benzene. You put butyl attached to benzene. When you react it here with this, everything there converts to COOH. We have this. This reaction can be found under the preparations of carboxylic acid. Right? So this is benzoic. This is benzoic acid. Okay. Now, let's look at question number 33. Okay, so let's start question number 34. Now, the question number 33 rather says, in amines, in anions can be prepared by reaction of the secondary amines with that. Plus, the answer here is alkynes and ketones. Now, when alkynes and ketones react with primary amines, when alkynes and ketones react with primary amines or amines that have two hydrogen, what we use to form here is imine. Right? Sometimes some of the imine is called ski base. So when it reacts with primary amines, what we have is imines. But when it reacts with secondary amines, what we have in amine, that means that guy will have an amine and a double bond. So the answer to that question is, in amines can be prepared by reacting aldehydes or ketone with secondary alcohols. That means in amines can be prepared by the reaction of secondary amines with okay, please in order not to make a mistake here, like I said, I'll drop the answer on the comment section. It's actually about trying not to mix the compound. So this number is 3. Alright, text 4 says provide the structure of the products formed when propane is hydrated with sulfuric acid in the presence of mercury 2 ion. Now, this particular reaction is under reactions of alkynes, addition of water. So when we have propane, this is CH3, CH2. No, this is propane. Hydrated means you react with water. You know, they are supposed to tell us when alkynes react with water, but they are being very illogical. Hydrated means reaction with water in the presence of dilute sulfuric acid, H2SO4, and mercury 2 ion. Alright? Now, this reaction is going to give us enough first, and then isomerism will take place to give us a ketone. So what is going to happen is that water is going to break as OH and H, and carbonyl fluid is going to happen here. The H goes to the carbon of the triple bond that has more hydrogen, and of course it's going to be carbon 1. So the H goes to carbon 1 and the OH goes to carbon 2. So it becomes CH3, COH, double bond, CH2. Now this is enough, right? Remember when we started in this part, question number 2 was isomerism. Now, enough can be, this guy is going to convert directly to a propanol. So how do we get this? The H of the OH adds to this guy to form CH3. and this double bond goes to this. So the reaction is going to be CH3, this. So this is the end product of that reaction. It cannot stop at this. This is propene 2-up, and this is propanol. So take note of this. Anytime alkynes react with water, the water is going to add following the Markovnikov rule. The H goes to carbon that has more hydrogen, and the OH goes to the. When you do that, you're still going to have a double bond left. Now, this is an enol compound that contains a double bond and an alcohol. Right? This is now going to be arranged in a very fast, order to give a ketone a propanol. So that is the answer to that question. So the process here is what we call the tautomerism. Okay, now question number 35 says, draw the structure of two bromo, 2-chloro propanoic acid. Now, first you start with the parent name. Propanoic acid is 3 carbon 1, 2, 3. Alright, you have COOH. On carbon 2 we have chloro. On carbon 2 we have bromo. This becomes CH3. Alright, so this is the structure of this. Now, so far from this past question, it simply means that last year exam was a bonus, a piece of cake. Right? So if you actually follow the concept of CHM260, you realize that this guy is very, very simple. Many of us are having challenges on this. Please check our videos and perhaps join our marathon classes to get yourself prepared for exams. Please go. Is let me play.